Dr. Jack Ferracane is a professor and chair of oral rehabilitation and biosciences at Oregon Health Science University in Portland. He earned his PhD in biological materials from Northwestern University. He is a founding fellow and past president of the Academy of Dental Materials and past president of the American Association for Dental Research. He is recipient of Wilmer Sounder Award from the IADR Dental Materials Group, the Founders Award from the Academy of Dental Materials, and the Hollenbeck Award from the Academy of Operative Dentistry. He is an honorary member of the American College of Dentists and the Oregon Dental Association. He is the inaugural editor-in-chief of the JADA Foundation Science, and he serves on the editorial board of 10 other journals. He has authored and co-authored several textbooks on dental materials and operative dentistry, and has published over 320 peer-reviewed articles. His current research interests are in developing new monomers for enhanced dental composites, basically studying the factors that affect biofilm formation around dental composites, and also the use of bioactive glasses in resin-based materials. His research is funded by NIH, NIDCR, as well as private industry. He is also actively involved in establishment and operation of networks designed to conduct dental clinical research in the private practice settings. So with that, I would like to, give the floor to Dr. Ferracane and welcome him and welcome everyone to this nice opportunity. Thank you, Dr. Jack Ferracane. The floor is yours.
Thank you. Yeah, my pleasure. My pleasure to be here with you all, and thought we would talk a little bit about bioactive materials, and I put it in quotes. I always do this because I think we don't have a perfect definition of what bioactivity really is in dentistry, but we'll talk about that and what their potential use might be in bonded dental restorations if we can decide actually on what bioactivity is. So I'm not, don't have any conflicts of interest with any companies. We've done a lot of product testing and research for a variety of companies over the years, and they're listed on this slide. But I am a paid employee from the American Dental Association. And that relates to, as Dr. Manso mentioned, our new journal, JADA Foundational Science, all open access online only. And you can get to us at jadafs.ada.org. And we're in our second year and doing very well. So I'm going to talk a little bit about what we might be seeing as a new era for dental restorative materials. So I believe we've gone from the situation where we were really working to get biocompatible materials. That was the key thing we focused on, into what we now call, again, this concept of bioactive. And I wrote new in the title here, but that's probably a misnomer because the first papers in dentistry in which bioactive was used to describe dental resin materials back in 1988. So I want to spend a little time talking about what is bioactivity and what makes a material, or what would make a material bioactive. So I'm going to follow this outline. We're going to do a little bit of background, talk about why we are looking for alternatives or new restorative materials. Why are we even worried about this? And then I'm going to explain, in my mind, what bioactivity is from the standpoint of a narrow view and a broad view as we look at these molecules. I'm not sure if you can see the cursor, but we look at material.
Yes,
okay, great. Thank you. So as we look at either additives or molecules that are either releasing ions or containing molecules which we consider to be bioactive because they have a certain effect. And then we'll look at bioactive materials as they're used in a variety of applications, such as in pulp capping and vital pulp therapy, as restorative materials, as adhesives and sealants, and also in cements. And when we talk about this, I'll break this into two areas. One, antimicrobial. And now this could be anti-fouling materials, or it could actually be bactericidal. We're seeing examples of both of these. or we also could say anti-biofilm, and then mineralizing materials. Sometimes we'll call this remineralizing, but these are ion-releasing materials, and then the concept of biomimetic remineralization of a demineralized dentin structure. And then we'll draw some conclusions. So I'm going to spend most of the time kind of focusing in the area of composites and adhesives, although I said we'll talk about some of these other things as well. So I just thought it'd be good to just remember where we are at here. We have inorganic filler particles that are bonded to a polymer matrix through the use of a silane coupling agent. And we add catalysts and pigments in order to make them curable and to make them aesthetic. And we produce a paste, which we can package in a compule or a syringe. And we use these materials with a resin adhesive. So if we look at this material, we have a variety of opportunities for, again, our quotes, bioactivity, unquotes. We can make the adhesives, we can modify the adhesive formulation, we can modify the composite itself by changing the fillers or making different monomers or other types of additives to the system, which can provide for us this potential for bioactivity. So as I mentioned, we're still search for better materials. And I think this sums it up. The main reason for replacement of dental composites has not changed in over 40 years. And it's basically secondary caries and fracture. There are other reasons why they fail, but those are the predominant reasons. So we see instances of recurrent caries or instances of fracture restorations. And what has been found and shown in the literature is that the primary place where composites, especially class 2 composites, fail is along the gingival margin area. And it's because it makes sense. It's a logical place because it's a difficult place to place the restoration and also difficult to keep clean. And we wonder, is this a problem with bonding? Is it placement or is it actually bonding? So there's a couple of nice articles. This was written by Flavio DeMarco and his group and Nick Opdam. And this was published in 2012, The Longevity of Posterior Composite Restorations, Not Only a Matter of Material. So it gives us some idea that it's not just the reason the materials are not failing just because of themselves. There's other things going on. And they followed this up this year with longevity of composite restorations. Is definitely not only about materials. So sort of in summary, the second article reported about studies from 2011 to 2021 over a 10-year time period. The studies had to be 5+ years in duration, and there were 33 articles they looked at. And what's rather interesting is that the annual failure rates for posterior composites ranged anywhere from less than 0.1% to almost 5% in these studies, with survival rates being anywhere from 23 to almost 98%. And again, they found secondary caries and fracture being the main reasons for failure. But you see this wide difference in terms of survival of restorations based upon a number of different factors. So as again, we said, the main area of concern is the gingival margin. And we did a study years ago. Craig Vanderwall did this for his master's thesis while he was in the Air Force with Tom Hilton and Ron Sakaguchi, Bob Erickson, and I. They basically placed class 2 slot prep restorations, embedded a ball bearing in them so that we could thermal cycle these materials, we could mechanically load these restorations, and we could soak them in water for various periods of time. And what he wanted to determine was how much light energy do we have to provide to keep this gingival margin intact during all this activity. And we took impressions and made replicas for electron microscopy before and after. And you see this type of washout of the composite here at the gingival margin, which is very reminiscent of what is often seen clinically, where we see decay forming in this same area. And the study showed he needed about 24 joules per centimeter squared for adequate curing of the gingival margin, so this wouldn't happen. So there's several variables, the placement of the restoration. So how well this material is adapted to that margin, and then extremely critical is how well cured it is. And these are in the hands of the practitioner, the dentist. The patient also has a role in this because they have a saliva, they form biofilms on these restorations, and they age with time. And they are the ones responsible for interfacial stresses due to mechanical forces or due to thermal loading. And then the materials themselves, which are produced by the manufacturer. And in part, we think the deep bonding may be a function of the stress that's produced in the material during curing. And this is all a part of the manufacturing process and the formulation of the material. So everybody has a role essentially in how well this restoration does or does not do. What we found out more recently is the fact that even when we have a good bonded situation, we may have degradation of this bond over time and opening of gaps because of the effect of biofilms on composite restorations. Composites are good surfaces for biofilms to form. And so this is a little experiment that was done by Dr. Musashi for her PhD, in which a composite was placed inside of a dentin cavity. And what you're seeing here is the replica of the surface. And you can see this is the nice tight margin. And in both cases, before and after exposure of the restoration to just media alone, bacterial media alone. And the margin holds up very well. In contrast, this is the before and after for the restoration when it was exposed to a biofilm for a period of, I think, 1 to 2 weeks. And you can see a dramatic breakdown of the margin because of the biofilm causing degradation of this interface. So if we're going to try to make an ideal bonded dental restorative system, I think it has to have certain characteristics. It should be a durable bond, should be acid resistant and enzyme resistant. It should be bulk curable with low shrinkage stress and good handling. We should be able to seal all margins and potentially make the material mineralizing for demineralized areas adjacent to it. And antimicrobial would be great. It should be able to protect the pulp and possibly even repair dentin that has been damaged due to the caries process. It should be self-adhesive and non-degradable. And the material itself should be tough, strong, stiff. It should be hydrophobic. And ideally, it would repair itself when it saw cracks. So this would be an ideal bonded dental restorative system. So we think about this and we say, well, we have a lot of opportunities for a bioactive material to participate in this ideal restoration. So it's interesting to think about all the different ways we talk about this bioactivity and the words we're seeing used. So we have biomineralizing, we have bioceramic, biomimetic, biomodifying, biointeractive, bioinspired, bioinstructive. I've seen all of these in the literature or in advertisements which relate to this concept of bioactivity. And it all got started really with the development of bioactive glasses, which were amorphous materials based on a silicon oxygen tetrahedron containing a variety of ions. And it was developed by Dr. Larry Hench when he was at the University of Florida. He made a melt-derived glass, which was highly reactive. By what I mean by that is it releases ions into solution. Calcium phosphate could release fluoride. And the main purpose of this was basically, if you have the bulk glass, you will get ion release and movement through the surface, leaving behind a silicon oxygen-rich surface, but depositing ions at the surface, which can begin to precipitate new mineral. And at the same time, interact with osteoblasts, which will then become actually embedded, their proteins being embedded within the calcium, new forming calcium phosphate, and form a bond to basically new bone as it forms. So the concept of bioactive here was really with respect to mineralization and bonding to bone. We started working with John Mitchell many years ago on bioactive glasses. John brought the technology from Ohio State University to us here. And this was a study that was done by a fellow colleague from Korea, Duk-Soo Kim. And the idea was, can bioactive glasses actually mineralize adjacent demineralized dentin? So set up the experiment. We basically took dentin surfaces and exposed them to phosphoric acid so they became demineralized. We then basically attached it to a composite with a gap. In one case, the composite was just a traditional type of composite. In the second, the composite had bioactive glass particles in it, similar to the Hench formulation, but we make our own. And in the fluid gap, fill the gap, which either simulated body fluid or phosphate buffered saline. And this sat for about a week or two. And to start off, to determine what was happening, we measured the hardness. So they measured the hardness of dentin, solid dentin, and you see it's about nearly 70. And then the hardness of this demineralized dentin is about 42, so about 30 units less. And then after the experiment, measured the dentin that had been exposed to the composite with the bioactive glass, we found that about almost 40% or so of the loss of hardness had been recovered when adjacent to the composite with the bioactive glass, but not to the composite which did not have the glass. And if we look at this from an electron microscope view on a relatively lower and higher magnification, we see the surface before, the dentin surface before, with the demineralized tubules. We see when it's exposed to a composite that did not contain the bioactive glass, looks very much the same. And then when it was exposed to the composite containing the bioactive glass, where we see this deposition of mineral all along the surface within the tubules, et cetera, which would help to account for this recovery. Now, it's not perfect remineralization of dentin, but it is mineral formation, which produces this recovery of hardness. And a similar study was done by Arzu Törsvergil-Mutlue in Finland, looking at bag and fluoride-containing bag resins adjacent to dentin. So the question for you all, is this a demonstration of bioactivity? It is a mineralization process. So we go back to the question of how do we define bioactivity? So there's been a couple of attempts to do this in the dental area, and this is an article from Pekka Valatul and David Watts. Bioactive dental materials, do they exist, and what does bioactivity mean? And their conclusion was that materials that release substantial ions for specific biomineralization in the clinical environment. And then we have an alternative view from Dr. Brian Darvell. His title is Bioactivity, Symphony or Cacophony, a Personal View of a Tangled Field. So suggesting this is relatively complex in terms of how we interpret bioactivity. His conclusion is that a material must serve as a vehicle for biologically active substances that promote reparative or regenerative responses. So on the one hand, we have a focus on the biomineralization, somewhat similar to the original Hench bioactive glass. And on the other hand, we have a focus on a biological process being involved. So we move forward a little bit in thinking about this biological interaction. And here's a study that was done by a colleague, Paul Cooper and Yusuke Takahashi, looking at the dentinogenic effects of extracted dentin matrix components digested with matrix metalloproteinases. So the concept here was that these dentin matrix components that are found in dentin and released when exposed to an acid have been shown in vitro to upregulate wound healing in primary pulp cells, and in vivo as a pulp capping agent to stimulate tertiary dentin formation. So if we could think about this, one way of having this happen, we have a caries progress. It produces acids. The acids are demineralizing the mineral of dentin, and that process releasing these dentin matrix components, which were there from the time that this tooth was established in the first place. Now, there's also MMPs, matrix metalloproteinases, released at the same time. They can then attack and degrade the dentin matrix components and digest them. And those digested components now can activate cells, either odontoblasts or undifferentiated cells within the pulp chamber. And we can get the formation of a reparative or tertiary dentin. And it seems like that MMP20 seems to be very effective in stimulating this wound healing response of the dentin pulp complex. So it leads to an interesting question and a consideration. As we put acid on the tooth via etching or via priming with the self-etching system, we will release biomolecules from that surface. And these molecules can have a significant effect. The question is the acid bioactive, or is it the released molecules? So the acid releases the dentin matrix components, these proteins, also MMPs at the same time. The MMPs enzymatically act on the proteins, degrade them, producing components, which then stimulate cells. So it seems like a truly kind of bioactive activity here. So we did a paper a while back looking at dentin as a bioactive extracellular matrix. This was Tony Smith and Paul Cooper. And it was to sort of basically review what is present, what is being released from dentin when exposed to acids or EDTA or even calcium hydroxide and MTA. And you see TGF-beta and VEGF and DMP1, osteopontin, and a variety of different things, including the MMPs and beta-cathepsin. So this is Tony and this is Paul, and everybody was talking about this at the time. So here's Paul talking to the Queen of England and Prince Philip all about it when the new school at the University of Birmingham was opened. So preceding this, we had written an article in 2010, Can the interaction of materials with the dentin pulp complex contribute to dentin regeneration? And in that, we were finding similar things, that we could take these molecules and cause undifferentiated cells to become differentiated and to express markers for mineralization. And it got us to thinking, we have a tooth and we've cut, let's say, various depths of a cavity preparation, even up to the point of an exposure. And we know that if we now were to apply an acidic molecule, like an adhesive on this, we would release dentin matrix components, shown here, the native ones as red circles. But if we were to dope the adhesive or the acid with also additional dentin matrix components, we could really bring a lot of molecules to bear here to stimulate odontoblasts or to trigger a differentiation of cells within the pulp. And then we would this is again a part of an adhesive system. So by stimulating the odontoblasts, we have a reactionary dentinogenesis process. And by stimulating an undifferentiated cells, which cause them to differentiate and then begin to lay down mineral, we get a reparative dentinogenesis process. So the fact is that these dentin matrix components, whether endogenous or exogenous, can participate in the formation of reparative dentin. And then the question is this a demonstration of bioactivity? So as we look into this new era, if we will, for dental restorative materials, and as I mentioned to you in the beginning, we break this up into two different categories, one involving the oral microbiome, and the other will involve mineralization process. So if we take our bioactive material and we think, what kind of effects can we see from an antimicrobial? Well, we might be able to just prevent the adhesion of bacteria to surfaces. In other words, anti-fouling. Or we might actually have a toxic effect and actually directly kill bacteria, potentially indiscriminately or potentially discriminately. Or we can just prevent the dysbiosis that occurs by favoring the commensal bacteria as opposed to the more virulent ones. Or we can prevent the formation of biofilm. So we might have bacteria adhering to the surface, but we can somehow disrupt the formation of the biofilm itself. Or we can actually disrupt the film once it has formed. So our materials may be capable of doing any of these different things if the formulation is correct. Now, if we look at it from the side of mineralization, we can either prevent demineralization by being acid neutralizing. We could prevent demineralization by just modifying the ion balance in the environment, or we can actually mineralize and replace lost mineralized tissue. So this brings me to my concept of the broad versus the narrow view. So we'll start out with the discussion of what bioactivity might be if we took a broad view of it. And the FDI came up with a policy statement on this recently because they were asked to do this. And Gottfried Schmalz and Reinhard Hickel and Richard Price and Jeff Platt all participated in this paper that was published earlier this year. And they said that there were 5 criteria required for bioactivity. Basically, there has to be a mechanism, documented effect, a stated duration, there can't be side effects, and it needs to restore form and function to the tooth. So they said a bioactive restorative material should have beneficial desired effects. These effects should be local, intended, and non-toxic, and should not interfere with the material's principal purpose, namely dental tissue replacement. So the key thing, and why I say this is broad, is the mechanism is not defined. It could be biological solely, it could be chemical solely, or it could be a mixed biological and chemical mechanism. And now if we take a look at the more narrow view, we look at the journal, Bioactive Materials. Well, how do they define themselves? Bioactive materials will feature adaptiveness to the biological environment, being designed to stimulate and or direct appropriate cellular and tissue responses or control interactions with microbiological species. And then we had a conference several years ago, and Richard Price and Jean-François Roulet published an article with basically the consensus of the conference that dental restorative materials may be called bioactive. In addition to their primary function of restoring or replacing missing tooth structure, they actively stimulate or direct specific cellular or tissue responses, or both, or they can control interactions with microbiological species. So very similar to the Bioactive Materials Journal, but focused on dental and restoring and replacing as a main function of these materials. So this is a narrow view, and it has to involve biology. So if we look now at the materials, our potential bioactive materials, and I mentioned we could have sealants, adhesives, restoratives, pulp capping. We could also make cements. And we're going to look at this for the purpose of this discussion from the broad view, where the mechanism could be biological, chemical, or mixed. So I did a little looking in the literature to see what kind of additives have been applied to adhesives or restoratives for the purpose of producing bioactive materials. So we have adhesives and restoratives, and these are the items, and I'm sure there's more. I don't think I saw everything that have been added to adhesives or restoratives to make them bioactive, to do something in the oral environment aside from just restoring the tooth. So there's been a tremendous amount of effort in doing this. Very interesting, and we'll try to go through some of this a little bit here. So here's the concept of antimicrobial resins, which typically have been quaternary ammonium monomers. Probably the most popular example is the MDPB molecule developed by Satoshi Imazato and Karari produces and as a part of their Protect Bond material. So the idea, and Fightback is another product that is coming on the market that was work from Franklin Tay. The idea is that the molecule itself is positively charged as a quaternary ammonium. It reacts with a negative charge on the membrane of the strep mutans bacteria and disrupts the membrane, and the bacteria is therefore killed. So it's a contact kill. The bacteria have to come in contact. There's no molecule being released by virtue of the fact that it has a carbon double bond to bond it to the resin matrix in the adhesive or potentially in a composite. And here's another example of one of these molecules with a very long carbon chain attached here. Now, this turns out to be pretty critical and shown in a number of different studies that this material is most effective when this chain is about 12 to 16 carbons in length. This is just the depiction of live dead assay of biofilm on a surface of a control material, green meaning it's pretty happy. And here it is on the surface of one with a quaternary ammonium at about 10%, showing a lot of dead bacterial cells. Further studies in this area, this is by Anna Paula Fugolin in our laboratory here, looking at trying to understand this concept of a chain length. And she did very nice work looking at its effect against S mutans with a 9-carbon chain and a 14-carbon chain attached to the quaternary ammonium. So this is an example of biofilm. If you just look at this violet stain, the control looks like a very nice biofilm, very nicely colored. This is with the biofilm growing on a 9-carbon molecule, and it looks just like the control. It's obviously the bacteria is not being killed. It's very healthy. And then growing on a 14-carbon chain molecule, and you see we don't even grow a biofilm. So it shows, again, the evidence for the length of the chain being very important. Now, I want to put this into an adhesive material. Showed here's the control situation. Here's the 14 carbon chain monomer after 24 hours and after 6 months. And although there is some decline, it wasn't significant. So in general, we have durable bond strength even after 6 months. There's other literature looking at imatazolium containing resins in a similar way, but these are used as antifouling, again, to keep the bacteria from even attaching to the surface of the material. So the question is, does this work? So we have a little bit of evidence from Clearfill SE Protect. Again, it's this quaternary ammonium monomer. And this study that was published in 2014, looking at different restorative materials and their effect on secondary caries development in situ. So it's a denture model system where you set up sticks that are bonded to dentin with different materials in them, and then determine the mineral loss in the dentin, which is the white areas, in comparison to the control. You can see here, this is the mineral loss. And basically what they found was that amalgam showed similar surface mineral loss in adjacent dentin as composite, just traditional composite, but that composite bonded with Protect bond had lower surface mineral loss as shown here. So some clinical evidence that the effect of the molecule on inhibiting somewhat the bacteria and its demineralizing effect. Another area that's getting a lot of focus is the concept of Zwitter ions, where you can have a molecule which can either be kill bacteria or an anti-fouling surface. So for example, we have this carboxybetane ring, and in this case, in the ring mode, it's a bacterial killing. Again, bacterial is killed by the positive charge on the nitrogen. Whereas if it's an elongated state, a non-ring mode, it's bacterial repelling. So this Zwitter ion, this transition takes place, especially when it's in a solution. So here's an example of on a dry surface, the material is bacterial killing because the ring is closed. When the surface becomes hydrated, the ring opens up and basically it ejects or removes or keeps the bacteria from sticking to the surface. And the interesting thing is this switch can take place in a mild acid solution, which is interesting to us because that's what we experience as caries might be forming and bacteria are producing acids. We get a mild acid where we can actually get a Zwitter ion to switch and actually repel the bacteria. So we see a variety of different antimicrobial monomers that have been tethered to particles and then put into commercial materials. And an example is the Infinix product from Nobio. So these are nanoparticles either made with polyethylene amine or silica nanoparticles. And basically what it is a quaternary ammonium that's attached to the particle. So again, it's going to stay within the resin. It's not released, but it could cause bacteria to either not stick to the surface or to be killed when it attaches to the surface. So there was a nice study done by Peter Reckman looking at demineralization prevention with such a material containing these, what they call QA silica nanoparticles. So the idea was to produce in this partial denture system, the composite material here, the enamel, and to look and to see what kind of a lesion forms here when we are exposed when the bacteria is exposed to a material that contains the compound. And what they found was that with Infinix, this material that contained the QA-SI, there's 3 times less mineral loss in the gap than it was exposed to a regular composite, which did not have this. So some clinical evidence that the molecules are actually doing something to the bacteria, not a complete elimination or reduction, stopping mineral loss, but at least a reduction. So we see other antimicrobial additives as biofilm disruptors. And this gets very interesting because we can have a variety of natural compounds. So we have resin from bees that like T-farnesol and apigenin, which are anti-biofilms or anti-fouling types of materials. And what seems to happen, actually they break down the biofilm as it forms, or it prohibits the biofilm from forming because they inhibit the process of this glucosyl transferase activity. So in other words, what happens is the biofilm can't form these insoluble glucans that hold it together. And so instead, the biofilm is constantly being disrupted and not forming well. Then these are natural compounds that can do this, or obviously other synthetic compounds that can do it. And then we see orsolic and oleanolic acid, or trigonylene, which are truly antibacterial and plant-derived compounds. And they have these types of structures. And then we have polyphenols, which can be found in a variety of different materials like tea and cranberry juice, etc., that are, again, truly anti-fouling. They would keep bacteria off of surfaces. So then we start to look at also antimicrobial from ion releasing. Now we know plenty about silver and its effects on killing bacteria. Silver nanoparticles have been used in a variety of different materials. They cause tooth structure to stain, and that was the genesis of looking at zinc oxide particles, not quite as potent, but at least they don't have the staining issue. We have calcium phosphate nanoparticles, as calcium has an antibacterial effect itself. We have fluoride-containing materials, and we've seen fluoride actually produced and put into microcapsules in a material like BioCode from Premier, where it will have a slow release over time to give a constant environment of fluoride. And then some interesting work in trying to actually add something like chlorhexidine into a porous filler that could be added into a composite and would release this bacterial compound over time. If we look from the standpoint of remineralizing materials, again, these are typically ion-releasing materials, and glass ionomer and polyacids come up as the first idea, releasing fluoride and releasing other ions as well. And then we have the SPRG fillers that are present in Shofo's beautiful products, which are multiple ion releasing. So you have different ions that are being released from the surface, which can affect bacteria, and it's been shown to reduce bacterial adherence on composites. And then we have the calcium silicate compounds, dicalcium silicates, tricalcium silicates, and others, which also release calcium and will on the surface then react to form an amorphous calcium phosphate, which over time will crystallize into a hydroxyapatite. And there's been studies which show evidence for dentin remineralization, both in vitro and in vitro, and some evidence obviously of clinical success as we use these products very routinely. And these have become known as bioceramic materials. We have other calcium silicate compounds as well, but if we look at some of the literature with respect to these, we typically relied on calcium hydroxide. Calcium hydroxide, I would say, was the first bioactive material produced in the 1920s. And MTA has pretty much come along and sort of supplanted it. And we see for a variety of different reasons. We see studies which have shown that MTA and biodentin are more effective at remineralizing demineralized dentin in comparison to calcium hydroxide. And we see a study here which shows that there's a correlation between the amount of calcium released and an antibacterial effect, which again, we understand because calcium does have effect on bacteria. And these materials do, though, tend to be very biocompatible. And in this study, which looked at the different kinds of bioceramics and showed that resin-free pulp capping agents like biodentin or endosequence foster the formation of complete reparative bridges better than those with resin. And there's some question about whether there's some toxicity related to the resin that's used in these materials that makes them light curable. So we talked about bioactive glass, and so if we revisit this, as I showed you in the previous slide, we know these release ions and can form apatite. We had the original melt-derived glasses that release calcium phosphate and other ions, and these we find actually used in a variety of dental products like Sensodyne toothpaste, etc. And then we have sol gel glasses, and as I said, John Mitchell brought this technology to us. He would make his own glasses in a chemical process, not by melt-derived. They had no sodium in that at all, and they were actually nanoporous and would basically release a lot of ions. And we can see this is the glass, and then this is calcium phosphate mineral forming on the surface of the glass, which again becomes apatite in time. So these sol gel process glasses had very fast ion release, and we added them to dental composites at about 15 weight percent. And we showed that we could do this without a degradation in the properties of the material, and they had an antibacterial effect. These are the actual particles here. And we've seen some products on the market in which bioactive glass has been added for this purpose, but these were the like the Hensch glass, the melt-derived glass. But as I mentioned to you, bioactive glasses do have an effect on reducing bacteria, but they're not tremendously potent. We've also seen BAG added to glass ionomers. And a very nice review article a couple of years ago by Toscaya. So to just show you an example of some things we've done with this in the past, looking at bioactive glass, can it actually inhibit bacteria from progressing down a gap? So this is a dentin disc. We drilled a prep into it. We put composite, but not bonding it on half. So this is a gap formed in here. And we did this with different levels of different sizes of gaps, basically put it into a complex bioreactor system so that we mechanically loaded it after we had formed a biofilm on the surface and kept the biofilm alive, and to see what the bacteria does to this interface. And here's a section sample showing presence of the bacteria, and in this case, all the way down the gap. This is dentin and enamel, and the composite was over here. And this is confocal images showing for the control composite, which did not have a glass, bacteria shown in red on the surface, penetrating down the gap and actually across the pulpal floor. Whereas when we had a composite that contained bioactive glass, we inhibited some of the progress of the bacteria down the gap. So does composite with 15% BAG reduce biofilm formation in the gap? The answer was yes, by about 40 to 50%. With other mineralizing materials rely specifically on calcium phosphate. Calcium phosphate's been used in a variety of ways. Typically, it produces negative effects on the mechanical properties, though, and this has been an issue. But if you see this, we see amorphous calcium phosphate and the monocalcium phosphate monohydrate being actively used because they are highly ion releasing. As we go down the scale here, we go from highly ion releasing to very low ion releasing, as we expect as we get to hydroxyapatite, fluoroapatite, and octocalcium phosphate. Very difficult to get the calcium out. So we mostly see materials at the top of the scale being used as additives. Again, as I mentioned, mechanical properties tend to generally be lowered. A very nice paper back in 2016 by Drago Skirtic and Joe Antonucci on this. Now, this is last thing to mention is this concept of biomimetics. Polymer-induced liquid precursors. This is work from Lori Gower when she was back at UCSF, now in Florida, and putting polyaspartic acid soaking into a demineralized dentin surface. And this allows for calcium to enter and get sequestered and actually form mineral in an intrafibrillar pattern. Similar work from Franklin Tay's group using different protein analogs and a templating molecule. What he shows here is that here's the demineralized collagen. And if we don't get the imprinting molecules and the templating molecules in here, we'll form calcium phosphate on the surface. And that's not really a biomimetic material. But if we allow the material to soak in with the polyacrylic acid and the PVPA, we can now get calcium and phosphate sequestered intrafibrillarly and get mineralization to form there. So in conclusion, I would say in vitro and in situ, we have evidence that exists to support the use of antimicrobial and remineralizing materials, though for the most part, clinical evidence is pretty scarce. Our expectation is that current formulations may perform acceptably under ideal conditions, but likely easily overwhelmed by the patient factor in a highly caries environment. And bioactive materials can achieve an intended beneficial effect while serving their main purpose of restoring the tooth. And the mechanism can be either narrow in our strictest view, which must involve a biological process, or it can be in a broader view achieved through mechanisms that are biological, purely chemical, or mixed. And if I go back to my ideal bonded dental restorative material, In my opinion, I take the narrow view that dental restorative materials may be called bioactive if, in addition to their primary function of restoring or replacing missing tooth structure, they actively stimulate or direct specific cellular or tissue responses, or both, or they can control interactions with microbiological species. And with that, I thank you very much.